Hello everyone, in this video I'm going to solve some example problems on how to identify the Fourier transform of some continuous time signals. In particular, I'd like to give you some skills on how to plot these signals in the frequency domain if they're given in the time domain without taking the Fourier transform explicitly using mathematics. Okay, so let's take the first example. The first example is a cosine, and its argument is 10 pi t. Okay, in order to take it to take the Fourier transform and plot it, it's going to take you quite a while, and we use this plotting a lot in the frequency domain whenever we're dealing with communications and other fields as well. So that's why it is very essential to learn how to plot the cosine and other common functions in the frequency domain without doing the math, right? Okay, so how do I plot the cosine? The cosine in the frequency domain is a delta, okay, and actually it's a pair of deltas, one at the negative and one at the positive. But where are they located at? They're located at the frequency, which is 5 hertz. How did I know that it is 5 hertz? Because 2 pi f, okay, is equal to the angular frequency, and the t here is multiplied by the angular frequency. So that's the angular frequency divided by 2 pi, you get the frequency in hertz. Okay, so you multiply the entire number argument by 2 pi t to get the f. Okay, gives you the f. Okay, which is 5 hertz. So this is 5. And this is -5, and this is half and half. Why half? Because it is half of this coefficient, which is divided over these two deltas. Okay. Again, if it's a cosine, then you get 10 and -10. Okay, because here this is 20, and then you get 1 and 1. Because the amplitude is 2. If the amplitude was negative, then the deltas are going to be pointing down. Okay. All right. And if it's a sine, then you're going to get deltas as well. All right. So let's add these two signals. Then adding in the time domain is the same as adding in the frequency domain, and that's why you get the addition of the two graphs above. Okay. Let's take the fourth example. We have x4 of t is equal to sinc of 10 pi t. What is the sinc function? The sinc function is defined as sinc pi x is equal to sine pi x over pi x. And that's the definition that we're going to be using. All right? Why? Because there is another definition which comes from signal processing people. This definition comes from mathematicians, and this definition comes from signal processing people. What is that definition? It says that sinc x is equal to sine pi x over pi x. So I did not put the pi here, and it's implicitly meant to be multiplied by the x. Okay, so that's the second definition that I'm not going to be using in this video. I'm going to be using this definition. Okay. All right, sinc 10 pi x. I want to plot it first in the time domain, and then take the Fourier transform of that plotting. How do I do that? Let's plot it in the time domain. It looks like a sinusoidal function, but it's a decaying sine function. So that's the maximum amplitude, and that's the second maximum, and this amplitude is lower, and so on, so forth. It keeps decreasing. The amplitude keeps decreasing and keeps oscillating between the positive and the negative. What's the zero crossing? Where is it located at? It is located at the denominator of this sinc. What's the denominator? Pi t over 1 over 10. Okay, so that's the denominator of pi t is 1 over 10. Okay, 1 over the coefficient, and that's basically the location of the zero crossing, of the first zero crossing. The second one happens at twice the value, and so on and so forth, 3 times the value, and so on and so forth. And it is symmetric between the positive and the negative. And the coefficient here is 1, so that's why I get a 1 over here. That's in the time domain. Okay, so that's the t and the t. So what if we want to take the Fourier transform? If you do the math, you'll get a rectangular function. What are the coefficients inside and outside of the rectangular function? If you have a 10 multiplied by pi t, then the f is going to be divided by 10 and outside divided by 10. So if this 10, you get it and you divide, you divide by the f inside and outside. Okay? Division inside and outside by the 10. All right, so let's plot that. The plotting of the rectangular function, the amplitude is the coefficient, which is 1 over 10. Okay, if there's no amplitude, then the amplitude is going to be 1. And the width is the denominator. Okay, so here, this is not the width from here to here. That's the zero. The first zero crossing is the denominator of the sinc function. And similarly, the rectangular function, the width is the denominator, which means that this is 5 and this is negative 5, which makes this as 1 over 10. Which makes this as 10. Okay? All right. So what if I have a rectangular function in the time domain? So remember, this is the rectangular function in the frequency domain. Why? Because the sinc was in the time domain. Sinc in the time gets the rectangular frequency. What if I have a rectangular in the time domain? Okay, with a 10 at t. So what does that mean? How do I plot it in the time domain first? Well, I need to find what the denominator of the t is. The denominator is 1 over 10. Okay, so this becomes the width. 1 over 10 here becomes the width. 1 over 10. Half of it is 1 over 20 and negative 1 over 20 at the negative side. So that's in the time domain. Let's take it to the frequency domain. How do I do that? The rect turns out to be a sinc. If it's a sinc in the time, a rect shows up in the frequency. If it's a rect in the time, then a sinc shows up in the frequency. What's the coefficient of the sinc? Again, it's pi f. That's regardless. Okay, and here you have a 10 multiplied, then it becomes divided inside and outside. Right? So that's why I have here 1 over 10. And the 10 here, which is in the denominator, it becomes the first zero crossing. Okay? So that's basically why we call it, we call the rect and the sinc Fourier transform pairs. Because when one of them shows in the time, the other one shows in the frequency. And that skill, you need to develop this skill and learn these techniques so that you do not have to take the Fourier transform of some complicated functions as the rect and the sinc. Okay? All right, what if I have a sinc squared? Okay, what does the sinc square mean? It means sine over 10 pi t, and here 10 pi t, and all of that is squared. Right? So let's square the sinc function. So that's the sinc function. I squared it, so I took the negative and made it a positive. Okay? And the coefficient is 1, because that's 1. Right? That's the coefficient. And the zero crossing happens at the 1 over 10. Okay? Again. Right? It's the same as how you plot the sinc function. Okay, so what if I would like to take it to the frequency domain? It turns out to be a triangular function. What's the coefficient inside the triangular function? It's a 10 as well, divide inside and outside. The same law applies as well, but just by coincidence. Okay, so if you take the Fourier transform, you'll find it to be a triangular function with 10 here and 1 over 10 over in the coefficient of the tri. Okay, so that's the triangular function has an amplitude 1 over 10 because that's the 1 over 10, and the triangular function has a positive side equals to 10. Where did I get this 10 from? I got it from this number. Okay, so it's not the width anymore as it was the case in the rectangular function. No, right now it's not the width, it is the positive side. So the 10 here represents the positive side. Okay, so that you make a note of this so that you do not get confused with the rectangular function. Okay. Similarly, if I got a tri in the time domain, then I'm going to get a sinc squared in the frequency domain with the same formula, with the same rule applying as well. 30, so this becomes a 30. Okay. No, this is not a 30, this is a mistake. Okay. this is 1 over 30, and this is 1 over 30. Why? Because this is t over 1 over 30. Okay? So that's 1 over 30 and 1 over 30. And if I would like to do the math, the Fourier transform of the trie, I get the sink squared. 30 here is multiplied, so it's divided inside and outside. And remember, the square is not over the coefficient, it's just over the sink. Okay, and that's why this is 1 over 30 as an amplitude, and the zero crossing happens at the denominator. Okay? If you found this useful, if you found this video useful, please make sure to share it. Most likely other people are going to need it as well. And please have a look at the description. In the description of the video, you'll find a document. This document, I'm posting a link for that. Thank you for your attention.